in the last class, you have seen that and it is sometimes a relatively difficult concept to grasp. It takes some time to come to the terms with it, that functions can be treated as functions do not look like vectors. We have our mental pictures of things, and so it sort of contradicts our mental picture. I understand that. So that's why I'm going a bit slow. But you will slowly see the advantage of considering functions. Functions means well-behaved functions that do not go to infinity, normalizable functions as vectors. And I have shown certain similarities between functions and vectors, the way functions behave, the way vectors behave. And since from the school days you have been exposed to vectors, you will soon find that it is far easier to handle, to manipulate, to do algebra with vectors than with functions. And that is why we have chosen, in fact, Dirac showed us the way to translate sort of a feeling that these two behave similarly into the clear statement that these two actually are the same. And in doing so, we have, so we have seen that two functions, f and g, that means f of x and g of x, we never put the of x here, we only put the f and g, and this is nothing but your overlap integral. F star x this is the overlap integral. I suppose in the last year you have learned what the overlap integral, the concept is. Essentially, if you have a function like this and another function like that, and if you do this overlap, then in the parts when this function is 0, this total integral will be 0. In the parts where this is 0, the integral will be 0, and therefore it will only have a contribution in this part, the part of the overlap, and that's why this is called an overlap integral. But it is also true that if you have a function like this, and if you have another function like that, then for half, sorry, I've drawn it badly. Let me erase that and do it better. If you have a function like this and another function like that, then for half of this range, it will be a negative number, and for this half it will be a positive number, and therefore they will cancel off, and then we can say the overlap integral is 0. And in our mental construct, we will say that this represents a situation where there is a vector and there is another vector, and this overlap is nothing but the projection of it. So it is this amount. And when you move this one away and there is no overlap, then effectively it becomes like this, and there is no overlap, then there is no projection, and the overlap integral becomes 0. So you see the vector idea, and this one also will be seen in our mental picture like this. They are two orthogonal vectors. This mental picture has a lot of advantages, as we will show soon, but the main advantage is that we can do algebra with this kind of notations. If you have to do algebra, we have to have the rules of algebra. So let us work out the rules that will be followed. in this algebra. So we'll need to do some manipulation. By the way, we can easily see that this is a combination of two things. One is like this, and the other is this, as we have already seen, this is called the ket vector. And Dirac called this as a bra vector. So that when you put them together, this becomes a bracket. So these are sort of complementary things, ket vector and the bra vector. And you put them, you get essentially a bracket, and the bracket in our mind essentially implies a overlap integral of two functions. So let us now work out the rules of the manipulation of these. So the rules of manipulation. Firstly, if you consider the overlap integral minus infinity to infinity f star x gx dx, and then take the conjugate of it, what does it land in? This is essentially minus infinity to infinity f x. Now, if you start them, g will become star. Nothing but minus infinity to infinity g star x f x dx. All right. This means, it essentially means that if you have f g and you take a conjugate of that, that will essentially yield, okay, that is the first rule of manipulation we have learned. Now, notice one thing, we never put the star inside this. Whatever is in the left-hand side, whatever is in the bra, we know that that has the star. Okay. So, for example, here f does not have a star, but since it is in the left-hand side, we know that when you write the integral, it will have the star. It will be conjugated. The second, let me get some space. The second rule is that a constant can be taken out. That's because of the simple rule of the integration, because ultimately what we are doing are the integration. So the rules of integration will also apply here. F star x. Now, if you have here c gx dx, then you can take the c out. So it will become c integral minus infinity to infinity f star x gx dx, and I can write this result as f cg is equal to c comes out f g. Okay, so this is the result we have got. And if you put the c in the other one, minus infinity to infinity, it is c f x, this whole thing, star gx dx, that this is equal to, now notice, C will be start because C is a constant that could be complex number. So C will be start, Fx will be start. So C star will come out, not C. C star will come out. This implies that if you have C here, F, G, then what you get is C star comes out. Is that clear? So depending on where the multiplicative constant appears, whether it is in the ket sky side or in the bra side, depending on that, you will have either C coming out without any change, or if the C is in the bra side, then C star comes out. This is a rule of manipulation we have to remember. Third rule, the linear combination of functions. There also we know that the integral of a sum is the sum of integrals, and therefore we can, by that rule, we can write simply that f, say g plus h is equal to f g, that's by the simple rule of integration, f, sorry, it will be h. And if you have it in the other side, then also the same thing. It will be, say, g plus h f to g f plus h f. This is by the standard rules of integration, that the integral of a sum is the sum of integrals. Because of that, that immediately follows without any difficulty. Now, if g of x is a function that can be expressed in terms of some other function, say ci, gi of x summed over I, then let me get some more space. Then if I want to write f g, then this g is comprising these, and therefore we'll be able to write it as I c I f g I. Okay, so the breaking up of a function into its components also can be applied to these brackets. And similarly, if you have g f, then what will be? Now notice, the g was this. Now the g has come to the bra side, and therefore by the rule that we have already learned, you have to write ci star gi f and that is integrated over, that's summed over I. Okay. So we have learned certain rules of manipulation. On this, if there is any question, let us briefly break for a while and take those questions and then go ahead. Anish Acharya asks, sir, we have idea of the conjugate of a complex number, but what is the physical significance of the complex conjugate of a vector? Okay. Anubhav Nundi says, I think sir can't see your questions while presenting. Yes, I could not see while presenting. Well, when I always stop for a while in between and ask you to ask questions. Please ask the questions then. I cannot see the chat box while I'm presenting. I can never do that. Well, in any case, now you have pointed out, let me answer that question. So let me kill this and let me go back to the presentation. I suppose you can see the screen, right? Yeah. Now, you have an idea about the function and its conjugate. If I have, say, f, you know what is f star. That's what you mean. But what is the conjugate of a vector? Well, we are actually representing only f as a vector. And when we say that I take a bracket with f of g, because we are taking this in the bra side, we always have to write the integral that way. So it is a question of how we conceive. It is not we are taking a conjugate of a vector. We conceive this quantity as f g dx. Okay, so this vector is a vector. This vector is a vector. But when we consider this bracket, we know in our mind that whatever is in the left hand side, that has to be conjugated. It is just a rule of manipulation. If you keep that in mind, then we can do this. We never put a star here. Therefore, this vector is a vector. We don't put a conjugate of that vector in this position. No, we are not doing that. It is an operation between two vectors. It is an operation between two vectors, and it is just expressed when we express in terms of functions. We express it this way. Clear?
Yes, sir.
Okay. Let us give an example, and then it will be clearer to you. So let me erase this. But I suppose you have written this because we will use these rules in whatever we do now. Let me clear this part. Okay. Now we have seen that we can write a ket vector. Sorry. We have to write a ket vector, say a CG. So the vector was G, and C is a constant that is multiplied with it. Then we can, just by what we earlier did, we saw that if it is in the ket, it can be taken out. So it is C, G. And if it is a bra vector, and you have a C here, then you know that when you take out the C, it will be C star. Sorry, it's a bra. These are also rules of manipulation. And generally, in general, if we have the G written as, I just wrote, let me repeat, CI GI. So we are expressing G in terms of these vectors. Then, and if you can write the ket that way, its equivalent bra, that means G converted into the G bra, will be, again, it runs over I. It will be CI star. Sorry, again. So every of these vectors, these are the ket vectors, will have its corresponding bra vector, and we can again make a linear combination of these bra vectors to compose another vector, and that will also be a bra vector. Okay. Let me give an example that will be make these procedures clearer. So, example. Suppose I may need some space, so let me erase. No, let it be. So suppose your f function, f vector in this case, is, it will be I, say 0 to infinity, infinite number of vectors. It is a I, and this is phi I. These are the eigen functions. This way, sorry, not phi, it is p. Small psi was the symbol of the eigenfunctions. So, a particular wave function we are composing of the eigenfunctions. Now these will be seen as vectors, and these are the coefficients. So this is essentially what I wrote in the last class as any wave function being composed of a linear combination of the eigenfunctions. I've written it that way. Okay. And suppose another wave function G is given as I is equal to 0 to infinity. It is a I'll say Bi psi I. So these are the same in this case. These two are the same eigenfunctions. As you will see slowly that these can also be visualized as the basis vectors. So this is a basis vector, and this function, this vector, is expressed in terms of the basis vectors. This is a same basis vector, but with a different set of coefficients. Another vector can be expressed in this term. In that case, we ask, what is f g? This is what we are trying to observe. Now, G is here, but F was a ket, so I have to convert that into the bra. So, F bra, that is what we have to write, and then that will be I is equal to 0 to infinity. Now, AI has to be then, since it is in the bra side, it has to be conjugated. And these will be psi I. So once you have written down the equivalent bra of this given ket vector, then we can put these two together to make the bracket. So, but before I do that, before we compose this, we'll do another thing, because if both have the subscript I, then there is a possibility of inadvertently doing a mistake. So what I'll do is I'll change this subscript, and this subscript to J. This is a dummy subscript because so I can always do that. Yeah. Now we have to write this FG together. So I'll write from the left hand side. Sorry. FG and F is this. So I'll write I is equal to 0 J. F was J. Yeah. 0 to infinity. It is AJ star psi j bracket close, and then we have to write that it is I, sorry, has to be I is equal to 0 to infinity. It is BI psi I. Okay, now if you just multiply them together, you will find that there are terms like AJ star BI, and these multiplied together, there will be terms like that. So it will be a J is equal to 0 to infinity, I is equal to 0 to infinity. It will be AI star BJ psi j psi I. Okay. Now we know that psi, well, I had written j first. Psi j psi I is equal to delta ji, and therefore this is something that we know. This will become space, yes, I equal to 0 to infinity. It will become A, is that right? A, sorry, I had changed the thing. This will become A was J, B was I, like that. A J star B I, then delta Ji. Okay, and this immediately kills off all the terms for which I and J are unequal, leaving us only I is equal to 0 to infinity. It is AI star BI. Okay. Now notice that this was the bracket which was supposed to play the role of an overlap integral, and the way we have obtained is like AI star BI summed over I. Now this is quite similar to the dot product of vectors, right? For example, if you have A dot B, then what do you write? Basically write A1 B1 plus A2 B2 plus A3 B3, so on and so forth. Now you notice that this is similar, quite same. So in fact, if you have the same thing here, in place of F and G, you only have psi, then you can write psi as just by this, I is equal to 0 to infinity AI star AI, which is nothing but this is obviously what we already learned as the the norm of this function. If this is 1, we say the function psi is normalized. And what are these AI mod squares? These are actually the probability of finding the eigenvalue in the state I is the mod AI square. So if I am talking about the probability of observing various values of energy, then A naught square is the probability of observing the ground state energy, A1 square is the probability of observing the first excited state energy, and so on and so forth. And it is then required that the total probability of observing any value of energy is obviously 1. So this will become 1, and then we will see this, say this psi is normalized. Okay, so this is have now become somewhat comfortable with manipulation of this. Let me again go back and stop here and ask, allow you to ask questions. Do you have any question now? On this, do you have any question?
Sir, here
Yes.
F and G were on the same system, right? I mean the
Yes.
same potential function.
Yes, yes. F and G are two maybe two different wave functions.
Okay.
Two different wave functions. But later, finally, what I did was to obtain the norm of the wave function psi, and that came out as the summation of the squares, mod squares of the coefficients. Effectively, these are the probabilities of observation of each value of energy, and that is what we expect to see. And you can see a specific meaning of the word normalization, because the total probability has to be 1. Well, if you have no further questions, let's proceed. Let me.
Sir,
Yes.
if f and g are from different wave functions, then what will be the functional space? I mean, we define the functional space as the span of all the eigenvectors.
Whatever I have done so far is that I have taken the basis the same for both, right? Do I have it still here? Yes. The bases are the same, but f and g are two different functions.
Okay.
And then we have composed this. So what runs through is that the same basis, and the basis is defined by the kind of potential function that you take. For example, when you take the infinite square well, then the basis functions, that means the ground state eigenfunction, the first excited state eigenfunction, the second excited eigenfunction, all these had specific forms. And they had the character that their overlap integral would be always 0. Right? That is something that we did in the last class, so I'm not repeating. But in this case, I am only considering that they have the same basis. Otherwise, everything is different. So f and g can be different. That means these can be two different wave functions. But if you have the same wave function, then you can apply exactly the same thing and obtain the norm. So the bracket of psi with itself is just this. Clear? You know, when I was talking on the first day regarding the postulates of quantum mechanics, then I said that one important postulate of quantum mechanics is that anything, any observable is represented by an operator. We have a psi function, which is a complex valued function of x and t, and we have different operators representing different observable quantities. So there will be one Hamiltonian operator for the energy observation, position operator for the position observation, a momentum operator for the momentum observation, and so on and so forth. Now, one important thing that, an operator was operating on a function to give another function. But now we are picturing things as vectors. So operators will then operate on vectors to give a vector. So it is like this. So let me get some space. Here, psi, say, is a basis psi 1. Another basis is, say, psi 2. And suppose there is a function f which is dependent on the two bases. So this will be its projection here, will be the first coefficient times this basis psi 1. This will be the coefficient times psi 2 that will define my vector psi, f. Now, if I have an operator that operates on the vector, it will give another vector. So in general, it will give another vector, something like this. Suppose I have operated by an operator A, then this is A operated on F. So in your earlier mental picture, a function being operated on by an operator gives another function. Here in this mental picture, a vector being operated on by a operator gives another vector. So we can write, let me draw a line here to separate. So we can write A operating on the F function. So this is a vector. A operating on it is the same as the vector of A operating on the F function. So it is the vector of A operating on the F function. So this is a vector, this operator operating on the vector to give another vector, and this is the same thing as the function, A operator on the function, the whole thing picturized as vector. So it's the same thing. Okay. Now, you already know there is a very hard requirement in quantum mechanics. The requirement is that any observable thing that you can observe, that you can measure, must be a real number. So even though all the time we do everything with complex numbers, at the end of the day, when we make a measurement, that has to yield a real number. Now, how do we enforce that on these operators A? Well, one hard requirement is that the expectation value of any observable quantity must be a real number. Now, what is an expectation value? Expectation value of, say, the variable whose operator is this A, is the expectation value is given by the sandwich integral. The sandwich integral here is like this. It will be psi and the A psi. And this is nothing but, by this, it is nothing but psi A psi. So this is the sandwich integral written in the form of Bra and Ket vectors, and this represents the expectation value of the variable A. And this whole thing should be a real number. And if it is a demand that it has to be real number, effectively, mathematically, the demand is A is equal to, right? So that is the requirement. If that is the requirement, I can write in this form as psi A psi should be equal to psi A psi star. And we know that G F star is equal to F G. We have done that in the last class. So we can write this as psi A psi. This is basically this. And that will be, this will be A psi psi. So it will be A psi psi. If I express this verbally, it will, I have to say that it does not matter whether A operates on the right hand side or on the left hand side. It does not matter whether A operates on the ket or on the bra. This is then the requirement of the expectation value to become a real number. Now, any function, any operator that satisfies this condition is called, that means, sorry, let me erase and get some space up there. This is the definition. Huh? So this is definition. If an operator A satisfies the condition that F A G is equal to A F G. This is for any normalizable function. F and G, then the operator is said to be Hermitian. So this is the definition of Hermitian operator. Hermitian operator is anything, any operator, where for any normalizable functions f and g, this holds, which means that it does not matter whether I operate on the ket or on the bra. And it is immediately seen that since Hermitian operators yield the expectation value as real numbers, therefore any physically meaningful operator in quantum mechanics must be Hermitian. Okay, this is a very important requirement. And you might immediately ask, the function that we know of, are they Hermitian? Let's check. Let's quickly check. Is X Hermitian? How do we check? By actually writing out the overlap integral. So the sandwich integral, because we are talking about the expectation value, minus infinity to infinity. It is f star x. Here it will be the x operator, and this x operator is nothing but multiplication by x. So multiply x with gx dx. Now this is the same because x can be written here, x can be written there, and I can also put the x here. It doesn't make any difference in the integral. So I can write fx and x here, gx. And now since x is real number, therefore this x is also, sorry, here it will be a star. Yeah. And this can also be put like a star because this is the same as this. X is a real number, so x star is equal to x. And therefore we can write minus infinity to infinity x fx, this whole star, gx. So you see, in this case, we had operated on the right hand side, and in this case, we have operated on the left hand side. So this is where we have said f x operator g, or I'll just erase this because it is the same thing. Yeah, x operating on g is the same as x operating on f. So x is obviously a Hermitian. This condition is satisfied. This condition I just wrote here is satisfied. Well, for x, it is not very surprising because x itself is a real number. And your immediate question would be that what about p? P, is, of course, has inside it a complex number. Therefore, what about p? Will it still be a Hermitian? So let us try to do that. Will that still be a Hermitian? Now that is a question. So we are trying to figure out if px is Hermitian. So how do you do that? Same way. We will say first that p x f g, and we'll also have to write this one here. But let us just figure out what this is. This is minus infinity to infinity, and px is minus I h cross del x. You know that. And operating on f, so I can write f here. This whole thing starred because it is in the bra side, gx dx. Clear? Now let's try to see what happens if I write px in the right hand side, which is in the ket side. Minus infinity to infinity, it is f star x. Now I'll have to put this guy minus I h cross del x. Now in this case, it will be g here, dx. Are they the same? We don't know yet. So what I'll do, I'll simply subtract these two. So if you subtract these two, let me get some space here. If you subtract these two, it is p x f g minus f p x g is equal to, I can see that IH cross will come out, IH cross will come out. So let me bring IH cross up front. Minus infinity to infinity will be there. Now this, what remains is IH cross has been brought forward. So it is del F star del X from here, Gx, minus and minus here, so it becomes plus. So you have, and star has made this one plus. So it is plus F star X del X. Okay, this whole thing. Now, this is something that we know what it is, right? It is IH cross will remain, but this is nothing but integral minus infinity to infinity. It is del X of, it is just F star G, right? F star G, right? Yes. And then this I can write as IH cross. It will be F star X G X going from minus at the values of minus infinity to infinity. Now, we have already said that G and F are normalizable functions, and therefore at minus infinity to infinity both should be 0, and therefore this term at evaluated at minus infinity and infinity both are 0, and therefore this is equal to 0. If this is 0, these two are the same. And therefore, even though the P function contains the imaginary number, the result is 0. And therefore, these two are the same, and it is a Hermitian operator. Clear? Okay, we are running out of time, so we'll stop here and we'll continue in the next class.